Hello, everyone, and welcome to the third online event organized by FunctionalFest. We are a group of Italian developers in love with functional programming. And everything started when we dreamed of organizing a functional programming conference in Italy. And well, as you know, COVID came then. So we decided that an in-person conference was not a great idea. And so we decided to organize a series of online events instead. So our idea is trying to gather all the different souls and community which gravitate around functional programming, both in Italy and abroad, with the not so hidden goal to foster functional programming adoption. So if you care about what we do, about functional programming, remember to keep in touch with us. We are on Twitter at FunctionalFest. You can subscribe to our YouTube channel or also register to our newsletter on www.functionalfest.it. I would like to thank Double Loop, which is providing the technical infrastructure and the support to host this stream call. And our speaker tonight is Mathias Verraes, which I'm very glad to host. He is a consultant advising organization on designing and modeling software for complex environments. He teaches domain-driven design courses and curates the DDD Europe conference. And he's also the author of the Parser Combinator library, which is called Parsica. And that's exactly what is gonna talk to us tonight about Parser Combinators. One last remark before leaving the screen to Mathias. If you have any questions for Mathias, please ask them in the YouTube chat, and I'll be glad to bring the question immediately to Mathias, and he will be happy to answer. So Mathias, please go on.
All right. Thank you very much for the introduction and for inviting me, Marco. Yeah, so the story is basically the same. Suddenly it was a pandemic, and I had all my clients had canceled everything, and all the conferences had canceled everything. So suddenly I had a lot of time and no intellectual challenges. So what you do, you study some more Haskell, which is sort of my guilty pleasure. And then I was looking into Parser Combinators, and then the classical moment comes where you think, hey, could you do this in a language like PHP? And before I knew it, I published an open source library. So what we're going to talk about is just, let me share my screen. I'm going to sort of show you the very basics of what Parser Combinators are and how you could build your own. It's actually or quite simple. The complexity is, of course, if you start doing more advanced stuff, but that's what the library solves. And here are some things about me. I should have spelled that correctly. So I'm at verraes.net. This is my Twitter, Mathias Verraes, and parsica.verraes.net has the library. But we'll start just without the library and do some simple programming. So don't worry, it's PHP. It's not a functional language at all, but it has functions and closures, so you can do this sort of thing. So what is a parser? Well, it's really just a function that takes some input and returns some output. Put very simply, of course. So something like this: the input is some string, and basically the input is usually something less structured or unstructured, like a string. And we try to turn that into something more structured that we can use to do other things with. So this could be anything from just a simple string from some user input that we want to validate to complete programming languages or file formats or anything really. It doesn't even have to be strings. It could be bits or whatever. So, well, a simple function could look something like this. We have some input and return some output. Of course, this doesn't do much yet, but let's try a very simple one. For example, something that parses, the simplest thing we can come up with, a parser that parses the letter A. So I'll write a quick test. We want to return A, so that's our expected result. And then basically our actual, let's write that's our parser applied to some input. And that input here, let's keep it as simple as possible. That's the letter A. So how do we write that function? It's of course not very hard. Here we could just, this would probably already work now because undefined, oh yes, well, this should be input then. This of course doesn't do anything, but just to see that the tests are working. So what we want to do is check if the first character of that input matches the letter A, and if it does, we return it as the output. If not, then it then our function basically fails. So we can use head. It's simple utility function here that takes the first character of a string. We apply that to the input. If that equals our letter A, then we return that letter A, and if not, we can actually, we should just do it like this. We return that head again. Not very efficient, but doesn't matter. And if it fails, we can return false, for example. So now this should still work. And we can also write a test for the failure case. So we could write assert false, that if we run our parser function on another value, another input, that it returns false. So this is all working fine. Let me make a little bit more space here. So this is our very first parser now. It can read the letter A. It fails on letter B, so all is working nicely now. Of course, this is not very interesting yet, but we can generalize this now, right? So a parser is still something that takes some input and returns either some output or a failure now. And now we want to make that character that we parse configurable. So I'm actually going to rename this one to character, like this. And now we need some way to construct this this whole parser, and that's basically another function. So we can write now something that takes the character we're interested in. Let's just call it C, and then uses that as the value that we're going to compare against right here. Right, so we have two functions now. The outer function basically sets up the parser, and the inner function is the actual parser because it's some input and some output. So now we need to define our parser now. So we could now define it as character A. And you see this is already nicely declarative. Now we have the, it just says what we want to parse, character A, and that creates our parser. So this value is of course the inner function now. And now we can use it on our input here. And let's see if that works. I did something wrong. Let's see, parsers character A input. Did I? Well, that's a good start. Let's try again. Anybody sees what I'm doing wrong? Input.
Yeah, line 35. I guess you have to use parser instead of.
Yes, thank you. That's the one. I was looking at the wrong one. Yes, there we go. All right, let's get rid of this because we don't really need it for this example. All right, so we have now a general character parser that can be used for anything. Of course, we could put something else in here. Still not very interesting. So let's try something more advanced now. Let's work on our input first, because of course we might have strings that are longer. And maybe right now our use case is that we just want to check if the string starts with A. That will still work, I hope. Because of course we're only comparing the first character of the input. So that's still correct. If we were to do this, then our test would fail, of course. So, but basically we're doing nothing useful anymore now, because after we parse that first character, we cannot do anything with this. We're just throwing it away in our output here. So we'll need a little bit more structure here. And basically, I set up some types here at the bottom. So instead of returning the output directly, we're going to return a result type here. And a result is, well, it's basically the either type, right? It's if you know Haskell or Scala or any of those functional languages, of course, it's either a success, which contains the output, or it's a failure, which is basically just a wrapper for well, for nothing right now. In practice and in Parsica, you would use this, of course, to put error messages and other information about why the parser failed, etc. But because we have these types now, we can basically add some more information to them. So we can also keep track of the remainder now. And actually, I need to add some constructor here and some getters as well, I suppose. There we go. And then now we can start doing this. I'll give this a little bit more structure for readability. So we have our conditional, and now if it succeeds, if the head of our input matches the character we're interested in, we will return a success. And if not, we will return the fail. This one. And we'll also, in that success, we can now put the remainder. So basically the rest of the string that we didn't parse yet. So when we parse character A, what we want is basically this. Let's call this here result, because our parser will now always return a result type. And let's check if the output matches A. And we can check if the remainder matches BC, right? So we're effectively splitting up the string. And of course, we can do that by calling tail here. Tail takes everything but the first character of our input. Let's test that, and it's green. So this gives us some possibilities now, of course, because we can start using that remainder. And we can continue the parser on it. For example, if I had, well, let's do something like AABC, we could run our parser again. So this would be result 2, parser, and this time we're going to run it on the remainder of our, so the ABC here. And then if we test our result 2, we should get A, and here we should get BC still. So, and I did something wrong again, syntax, there we go. All right, so of course what we did now here, so we parsed the input, we got the first character of it, we parsed using the same parser, we now parsed on the remainder, which is ABC, and then we get A and BC. But this is all very imperative code, of course. We're just sort of doing this work. And well, if you've done any Haskell at all, that's a no-no, this sort of code. It would even be hard to write it. What you're going to do, of course, here, and this is why it's called Parser Combinators, is use combinators to combine parsers into bigger parsers. So what is a combinator? It's really just any function that takes other functions as arguments or returns other functions and basically combines them into other functions. So in the case of our parser, if we can combine 2 parsers into one, well, bigger parser, then that's a combinator. So we could do something. This here, what we've been doing is a sequence. Actually, let me return that because I'm going to do it differently. Now let's just assume that this works now. So now I want to basically combine 2 parsers. I want to sequence them. So it could look something like this. So a sequence of first parsing the character A, followed by parsing the character B. Here we go. And now we need to define that, of course. So, and then the result of that, it's going to be the same as before. We're going to parse the first character, throw it away, and then if that succeeds, we're going to parse the second character. Now, the previous code that I showed was actually very naive because it assumed that the first parser had succeeded. We're also going to have to deal with that. So if the first one here were to fail, so if we're doing this, for example, this one should fail. So here on this input, and that means that the second one shouldn't even be tried because it doesn't make sense to continue if the first parser has failed, because then of course it's not a proper sequence. So what does this look like? Well, it's a combinator, right? So it's a function that takes two parsers as arguments. So let's just call them parser 1 and 2. And then it will need to do something with those parsers. In fact, I'm going to use the long notation here because, well, limitations in the language. Let's not worry about that. So we're basically doing the same thing that we did inside. We still have to do a little bit of imperative code in PHP, but at least it's hidden now, right? It's abstracted away, making it very reusable. So we're doing the same thing, right? It's our result is, or our first result is the first parser applied to some input. And in fact, I'm doing it wrong because we can't do that yet. We don't even have an input. So let me actually revert. Yeah, I'll do it like this. So, and this is where I needed the function. So this is the one, this is the parser again, right? This is the first one sets up the combinator. The second one here is the actual parser, which takes some input, returns some results, and it's going to do something with that. So that will basically be what I was just saying. The first result is the first parser applied to the input, and we need to include that. No, sorry. Here. So the first parser is applied to the input. We have the first result. And now we need to first check if that result was actually successful. So I already set up this this type with an is success, so we can test that here. Is this parser successful? If yes, then we can apply the second parser. So the second parser is now applied to the remainder, of course, not to the input, but to the remainder of the input. And we already have that abstraction. We can just get that from our result type. And of course, I also need to include this, which is a PHP thing for doing closures. If you use the long notation, you have to annotate the variables that you want to enclose. So if it's successful, we're now, if the first one is successful, we're applying it, the second parser applying it to the result. If the first one failed, there's nothing interesting we can do, so we just return the first result. So, and let me add some structure as well for readability. So now if we repair this code as well, what we expect now is we parse the first one, it succeeds. We parse the remainder, it succeeds, and it returns the B from our second parser in the output. And yeah, let's just try that. And that's green. So that's working. I hope this is making sense so far, because of course I cannot see and I have no feedback. So I'm just going to continue until someone stops me. Again, what we're doing is really just combining parsers into bigger parsers. And of course, to do that, we actually need to run those parsers. which is what we're doing here. We're actually running the first parser and then continuing with the result. But this gives us some structure and some some way of generalization, because we can now, as you can imagine, start reusing this sequence for all kinds of things. If you've done any functional programming, you might recognize this, because this whole sequence is actually the monadic sequencing. So in Haskell, that would be this symbol, where you're basically executing some action or some effect, and then not using the result, dropping the result, and continuing with the next effect. Well, it wouldn't be like this, but whatever. So yeah, basically we're doing monads in PHP now, and the underlying idea, if you think about it, what is the type of a parser? It's really you would write well, there's no generics in PHP either, so we don't have that. But it's basically the type of a parser is a generic with the type of the output. So our output here is always what's inside here, and so far that's always been string. But one of the nice things about Parser Combinators is that, of course, we can start having different outputs as well, because we can start structuring our input into a more useful output. This could be an AST, this could be all kinds of types, but we'll get to that in a moment. All right, so let's, of course, now we can check if the second character here in this input is a B, only if the first character is an A. So that's well, that's actually quite useful. But what if we want to parse the first two characters, for example, and we want to keep them both because we want to use them for something? So we need something like sequence, but our output should be something else. So let's write a test. So what we want now is a parser that, well, let's take this example, where we take the first two characters if they are A and B, and we put them in a list, basically. So in Parsica, I call that collect, because it's collecting the results in a list. But well, this could have different names in different Parser Combinator libraries. But we're doing something like sequence, but we need to not get rid of the A now, or the first parser. So how do we write the collect? Well, pretty much the same start. We have the first two. We have the first function. The outer function is the combinator that accepts two parsers and will return a new parser. So the outer, if we could here, because we're using functions, we cannot type them, but you can think of this as two parsers being combined into one parser. In fact, in Parsica, we actually have these types with some workarounds and stuff. So it's mostly functional with some object-oriented things in there, because they're unavoidable. But so here we have the two parsers, and we basically return a new parser. It's a parser, therefore it's always some input to some parse result. And now we need to figure out how to get that result. Well, we start the same way. We apply the first parser on the input, and we have that result. And then we will include it, of course. And then if that succeeds, we need to take the next step. So if result 1 is success, we can continue. If not, if the first one fails, there's nothing we can do. So of course, we're just going to return the first one. The value of this is, of course, a fail now. But so assuming that it succeeds, what do we do then? Well, same thing. We need to apply the second parser on the remainder. So parser on result1 remainder, and we put that in result2 because this time we're going to use that, of course. And now we have another conditional. If the second result is successful, then we can, well, I can actually write it like this. It's a bit more readable, in my opinion. So if the second one is successful, remember here our tests, we want to return, we want the output to be the first, the result from the first parser and the output from the first parser and the output from the second. So you might think that we're going to do this, result1, result2, but that's not correct because we need to get the outputs from it, but we still need to return a result and not just the output. So it's basically a bit of shuffling of values here. We get the output from the first one, the output from the second one, and then it's a new succeed, right? And if it fails, if the second one fails, well, what would make the most sense here is to return the second result, which is going to be a fail. Of course, now the fails, if you recall, they have no values or anything, so it doesn't really matter. But typically we would put in here an error message. So if you think about it, it makes a lot of sense that if the first one succeeds and the second one fails, that the error message would be the error message from the second one, from the failure. Because of course the first one doesn't even have an error message. And you could even do more clever things where you start combining error messages in some way, where you say, well, I expected AB, but I got a X, for example. Which is the sort of things that libraries like Parsica can do for you, of course. Let's see what I expected to be result. I thought that was the case. Implements result. Oh, succeed is something else. It's success. There we go. And we also need the remainder, of course. So same thing here. What makes sense as the remainder? Well, we already consumed the first character. We consumed the second character here. So what makes sense now is the remainder from after the second character has been consumed. So that would be the remainder of results 2, like this. And let me add some more structure again, like this. So I hope it's a bit messy here. We could probably make that cleaner, but I hope it makes sense. But just to reiterate, we try the first parser. If it succeeds, we try the second parser on the remainder of the first result. If that succeeds as well over here, then we return a new result, which is a success, containing the list of the two outputs and the remainder of the second result. And if it fails, we just keep returning the most recent failure, basically. So now our test should run, and that's green, so all is well. We should actually, I could show you that the remainders are correct by doing this. This was a C remainder. And that's green. What we could also do, of course, is test another case. So what happens if the second parser fails? So the first one succeeds, the second fails. What we expect is that this is a failure. So this would be a new fail like this. Or actually, maybe it makes more sense to do no, false. Where we check the result here. there's of course no remainder because we're not keeping track of that. But you could still do that. You could still track, well, not the remainder, but whatever is left. So here we consume the A, but you could keep the X and the C so that other things can continue from that remainder. But oh yeah, there is no remainder, so yes, that should work now. All right. So we've now shown that if the first one succeeds and the second one fails, it works. We can show that if the first one fails, then it also the whole thing fails, right? All right. How are we for time? Okay. Yeah, I can probably continue for a few hours, so somebody will need to stop me. So yeah, we basically have now two combinators, right? We have sequence, we have collect. We can start doing things with that. And the interesting thing here is, of course, as well that collect, the output of collect, the type of the collect parser here, or of this parser, is not a string anymore. It's an array of strings here, or a list of strings. But it's still, maybe not the most useful thing. But we can start, we can start working with that. Of course, we could first run this parser basically here, and then start transforming this into something we like. But the nice thing about combinators is that we can use all kinds of typical functional programming techniques and other combinators. So we could do something like map. So what is map? Well, you're probably familiar with that. It's something that can apply a function to some functor, to some structure that has a value inside of it. So in our case, our parser, you can think of it as a box that contains the future output. And map is applying a function to that, some kind of transformation. So an example of a function we're interested in could be string to upper. We want to apply that to the value that we parse. So I'm going to use, well, let's move that here first. And let's first actually write our test. So this would be our parser, which combines, let's just go back to the A example here, which combines the character parser with this function that we're going to map over it. And then if we apply that on our, my machine is hanging. There we go. If we apply that here, we would expect our A to have transformed in uppercase, and we don't need that. So how does it work? Well, it's just another combinator. So what's a combinator? Well, it's something that that takes, in this case, a function f, and it takes a parser p, and it's going to return a parser, which we cannot do this because we don't have those types, but you can imagine it. And then it needs to do something useful with these two things. So it's the same kind of thing again, right? We need to somehow run our parser, which is in itself something that takes input, returns some result, and now we can actually do the work. So we get the result from the parser applied to the input. If we need to include it, if the result was successful, if the parser succeeded, then we need to do something with that function now, of course. We need to apply it to the output. So we can get the output from the result, which is this here. We apply the function to it. And now, of course, we still need to return a result and not just our output here that we transformed. So we simply wrap that in a new success. And we also provide the, like this, the remainder, which we can just get from our results, like this. And if this whole, if this parser failed, P here, then we we simply return the original result, which is a failure now. And we include the F. No. There we go. And so now here, when we call map, we're saying take this function string to upper, take this parser here, whatever it is. Right now it's just a character parser, but basically any parser which has the type of string. So the output of this parser needs to be string, of course, so that we can feed it into string to upper. So take that parser, run it on some input, and then if it succeeds, we apply the function to the output, wrap it in a result. If not, we return the failure. And let's try that, and there we go. We are green again. Right. The nice thing about this is, of course, that we can do all kinds of types now. You can, well, if you've used parser grammars, which are basically languages that allow you to describe your parser, describe all the rules basically, and then you get some structure, but then you still need to do transformations on that structure to make it usable. The nice thing about Parser Combinators is that it's all one language. You just write, and it's all together. So you can just write in code, and you can write both the parsing and those transformations at the same time. So if you have some kind of big nested structure like a file format or programming language, you just keep putting these sort of maps inside different things and turn that into something useful. And then this map is just another parser, so we can combine it again with other parsers. In fact, let's illustrate that. We can do, for example, our collect, which collects the results of two parsers, a map of string to upper of A and another one of B, and like this. And now, of course, we expect our result to be two uppercase strings, and it still works, right? So this is actually a bunch of nested parsers now. You can imagine you can do all kinds of things with this, and this scales in terms of complexity because the way you start building a parser is just making these sort of combinations and give them some name that makes sense. Well, maybe this would be a good point for me to switch to using Parsica because I'd have to write too much code myself. So in Parsica, it's doing all these sort of things, but it's a bit more robust and has types, and we're using a third-party type checker as well that allows more advanced types than PHP normally allows. It's called Psalm, if anybody's interested. But so let's take something. What would be an interesting input? Well, we want to parse something like this, some money value, and let's have some type for it, right? So this could be class money, which is some currency. Let's just use strings, and some value. You shouldn't use floats, but I'm just going to ignore these kind of details now. So the value, and let's make a constructor for it. And so basically we want to parse this into some kind of, into this money object. So, well, we can use, let's take a parser. We can use our collect. Which I'm going to import from Parsica.
Matthias?
Yes?
Can I stop you for a second? There's a question.
Yes.
By Marco, too, not me. How does Parsica deal with PHP lack of tail call optimization? Seems like there's going to be a lot of function calls for which language is quite inappropriate.
Yes. Right now, it doesn't deal with it at all. The performance of Parsica is terrible, and we're not going to release a 1.0 until we find solutions for it. Some of the solutions will involve replacing functional code with more imperative while loops and go-tos for all I care. But so the inside will become rather ugly, as long as we can keep the outside very, very elegant. Things like recursion, there is actually a performance solution already, which is basically using a little bit of mutability, so it looks like this. You have your parser, which you define as recursive, and then you can actually do the recursion. And here I can now build my parser, so it could be I don't know, something, well, let's say a sequence of some character and recurse on, I don't know, this doesn't really make a lot of sense now as an example, but it looks something like this, and now you can actually recurse, and this is actually performant because it's under the hood, it's mutating this this parser object. So, and there's a lot of things where I believe we will be able to find solutions to make it performant, but so far we haven't worked on that because, well, in the beginning of the pandemic, I had time. Now all my clients have returned, and they need to use up their budgets that they didn't spend. So I have too much work, and I'm only doing this on Saturdays. So consider this an invitation to contribute if you want to use this. But right now, don't use Parsica for anything anything serious, right? If it's just a little, use it for little experiments and stuff, but don't. It would be too expensive in terms of compute. I hope that answers the question.
Thank you.
All right. So, oh yeah, we were parsing the money. So basically, we can do collect. The first thing, I suppose we could still just use the character parser here, and we need to import it, and we can use the number. Well, actually, that's no. Now I need to remember what we call it. Or maybe it's float. Yes. So the float parser, which basically will parse all kinds of this and negatives and what you call it in English, exponentials, stuff like that. So this should actually, we can just try that, of course. So result is parser. We need to do some, this is some Parsica stuff, but it's basically the same as we did before. We're just applying the parser, we get a result. There's just a little bit more syntax and stuff to do with it. So we're trying that on a string, and we can inspect the result now. I'm actually going to do just a little trick so I can use the debugger. And then if I run this, if I got that right, we should be able to inspect the result. So here you see now that our collect, just as before, has basically split up the input into two values. And now we can actually start using that. So, well, in Parsica, we have two ways of doing notation. We could do map, just like we did before, or we can use more object-oriented fluent interface where we call map on the collect parser. So here we can pass our function. This function takes that that output, so the two variable, the list with the euro sign and the float. So let's call it O, and it can now use these values to produce our new money object, which would we had currency first, so that would be the first value from the list, and then our second value, and let's add some formatting. So now if we run that again, must be of type float. Yes. So, well, here's something interesting. Of course, this parses this number. It succeeds, but it parses it into a string. So we could actually add another map here and cast it to a float. Actually, we need to do this, of course, function. This is the output. And so now we're basically doing two maps. The first map converts the string that was parsed into an actual float type. And then the second one creates the money type. We could do this in one step, of course. We could have just put the float file here. But just to show how you can sort of build up bigger structures this way. Well, there's no assertions, of course, but if we inspect the output, result output, we should here. We have a money object now that has the float and has the euro symbol. In fact, we would probably need to match this with something other than the euro symbol. We would probably use EUR. So that could be another map here or there. So actually, well, this is actually a nice pattern to do it. You could just do basically ignore the result, return the euro string, and I'll show you why in a moment. Let's see if this works for now. No, I keep hitting the wrong button. So our result now has EUR. And what you can do now is something like this would be a, well, it's not a really full-fledged solution, but you could do this and say, well, if we match this character, we will cast it to USD. Things like that. So you can basically build up like this. I need to change my input to test it. So there we go. Results, output, and now it's actually casted to USD. So the whole idea is you combine these parsers into more complex stuff. Like here, for example, if you were to write this in this way with this sort of list of different characters that we match, you could have stuff like this as well, right? Where we say if it's a string or a case insensitive string of EUR. So anything that is EUR will also map to EUR, etc. And now basically this whole thing is our currencies. So now I would just typically give that a name. We call that currency. The other one, well, let's just call that one value. No, like this. I need to map as well. Let's call it value. And now sort of the structure becomes really readable, right? What is our money parser now? It's collect a currency and a value, and map it to a money object. So it's purely declarative code. You just and this is the thing I love so much about it. You just describe what you want to parse. You describe the structure of the thing you're interested in parsing, and then you can just sort of keep combining this into. So again, building up, we could now do well, currency pairs. So currency pair is something like it's a ISO standard for conversion rates. So it typically looks like this: the source currency, the target currency, the exchange rate. I have no idea what the exchange rate is. Let's say this. So you could reuse our value and our currency parsers, add some stuff here to deal with the spaces, etc. And you have a currency pair parser, and we have another currency pair object that we can put it in, etc. So you can just keep combining stuff, and that's what I like about it. Yeah, I think we're out of time, right?
Yeah, I was just about to to say Matthias. And yeah, thank you very much. It was really, really nice listening to you talking about this.
Thank you.
And before leaving the closing note to Massimo, I would like to ask a question myself. Uh, so the question is, how was it implementing parser combinators in PHP? Which were the things which you said, oh, that's actually easier than what I thought, and which were the ones you said, oh, why am I doing this in PHP?
Yeah. Well, the thing I like is that we can still really just have the same sort of very declarative language, which people aren't very often doing that in PHP. So this, right? It's as close as you can get to just describing your structure and all these things. So that's something I was very happy about, that actually works and is scalable. Well, the things about performance, of course, that I already mentioned, are a bigger problem. Well, and then types was an interesting thing because there's a lot of stuff that you cannot do with types in PHP. But I mentioned Psalm, so it gets quite tricky. So if you look at, I don't know, here the types of things that we annotate with Psalm, this is a list of a parser, of a callable, of a parser, the expression AST. It gets a bit tricky, but Psalm itself works very well. So it's amazing that a type checker written in PHP for annotating rich types in PHP actually works that well and provides so much value. So that was a nice thing. And then, well, the sort of things we've been doing, like the expression parser is the most fun thing I've ever built, I think. Basically, it's a higher level language that maybe I should use some of these examples here. It's a layer on top of Parsica. It's still just parser combinators, but it allows you to define an expression language. So here we have a very simple AST. So this is our AST for Boolean expressions. This is the input, so it's just strings. And then writing a parser for that. Now, because of it, what's under the hood, you don't want to see it, but you basically say, give me you write your term. So here is our terms, right? Or term parser basically parses our values. And then we have parsers for operators like these. This is a unary operator, binary operators. You just define those, and then you build up. You use the expression function, and you build a list of these different operators, and the order is basically the order of associativity in nested structures. Maybe a better example would be, yeah, this shows it a bit better here. So this is a typical calculator here. We have our expression parser, which either parses parents with expressions inside them, or it parses a term. So this allows us to parse something like just a number one. This our parents, and then we have the highest precedence is the prefix operators minus and plus. Then we have the increment and decrement postfix operators. Then we have multiplication and division. Then we have addition and subtraction. And so it's working out the whole parser basically just from this. And the fact that we were able to do that in PHP is something that made me very happy. It's very slow still. There's some issues, but again, those will eventually be solved. That was a long answer to a short question, but
Better than a short answer to a long question.
I guess so. Any other questions?
Well, there was a question on the YouTube chat. Is it parsing hosted on GitHub?
Yes, if you go to parser.verraes.net, there's all the links. There's I wrote a whole bunch of documentation. I'm still trying to write some more. So it should be enough to get you started. And it's MIT licensed, it's open sourced, it's GitHub. So if you want to try it, go ahead.
So another question, if you can, is if you ever try to benchmark your library Parsica against any other PHP libraries.
I've played around with it a little bit. I did, but I haven't really spent time on it. But I basically used an existing imperative JSON parser that I found somewhere on GitHub. I wrote my own JSON parser, which well, an entire JSON parser in Parsica is this is all of it. So it's 222 lines here, or 23. And well, this is the, no, where is the, yeah, so it's, well, basically you can sort of see the structure here. It's a bunch of elements, etc. These sort of things. But so this entire parser, and basically I did some benchmarking comparing the Parsica one, the imperative one, and the native C library that it's included with PHP. And well, it was very sad, the results, but again, yeah, it's just something that that will need a lot of work first.
Okay, thanks. There's actually a question from the YouTube chat, which is, what's the level of type inference of Parsica itself?
Of type inference?
Yeah.
Or, well, if I understand the question, it doesn't actually do type inference itself. You have to, well, inside the library we annotate everything with Psalm, and then basically when we write code like these tests, this was an experiment for parsing Excel formulas. Just a quick, but we don't annotate any of this. We just write our parser. Let's see, where is the? Yeah, I forgot where it is. But if you look at all of these things, we just define the parsers without worrying about types. And Psalm actually does catch a lot of. If we make mistakes here, Psalm will actually catch your type errors. But if you really wanted to be sure, you'd have to you could annotate things in here as well. Like here, this this map function here. I should probably annotate this value here is a string, and the return type here is an integer. So I could annotate that for more certainty. I'm not sure if that's the question, but we've actually tried to, we're trying to make it so that you don't need to understand functional programming or advanced types or anything to start building your own parsers in PHP. But if you want to do very advanced stuff, you probably would need to dig into that. There's some stuff on the website as well about functional concepts and types, etc.
Good. So actually, we have a comment, yes, that answers the question from the author of the question itself. So
all right, excellent.
Very nice.
Anything else?
Yes, we have another question. As you're using recursion, are you having some PHP limitations when using too long strings as inputs?
Yeah, that's stuff we haven't really tried. The longest string I've parsed so far is maybe like a small JSON file or something. So again, I don't actually know how bad it gets for longer inputs. But well, the solution will probably be some kind of streaming. It already has some infrastructure to do that, but we haven't actually built it where you can like stream files from disk or whatever, and just parse them as they come in.
Okay, so I don't see any other question on the YouTube chat. Of course, let me thank Mathias for his talk again, and I really enjoyed it, and I'd like to give you a round of virtual applause.
Thank you very much.
Let me also thank Double Loop again for its technical support with infrastructure. And let me also remember you to visit our website on www.functionalfest.com or follow us on Twitter at FunctionalFest if you want to stay updated with next events and the next talks. And well, if you have any feedback or questions or comments about the talk by Mathias, please leave a comment in the chat and we'll see it. Okay, so thank everyone and bye.
Thank you very much.
See you next time.
See you.
Thanks, Mathias.